Title is Spacecraft Rover Hybrids for the Exploration of Small Solar System Bodies. Thanks.
Thanks, Jacob. All right, hi everyone. Like you said, my name is Ben. I'm a grad student at Stanford University. I've been working for the past couple years on an exciting project funded by NIAC, which seeks to enable small hopping rover hybrids for in situ exploration of small bodies. This is a project with a collaboration with JPL, Julie Castillo, Easton Nesnis, Andy Frick, and Robert Reed, and then Jeff Hoffman, a retired astronaut at MIT. So why do we want to visit small bodies? Well, I just put this slide up here to highlight some of the strategic knowledge gaps that small bodies target, but I don't need to convince this audience why small bodies are scientifically interesting. But there is an increasing need now to take more in situ measurements to complement what we've remotely observed. You can't constrain composition or physical properties of regolith from remote observations. So, moreover, bodies such as Phobos can't figure out the laser pointer. Bodies such as Phobos have been shown to have very spectrally diverse regions. So moreover than just taking a single sample like an OSIRIS-REx mission, we now want to take targeted samples from different areas around the surface. Phobos is lit up spectrally blue and red in different regions, and it'd be very interesting to take in situ measurements of these different regions. But the big question is, how do you actually achieve surface mobility in an environment that's much different than where we've been before, that is Mars and the Moon? So before I dive into our solution, I just wanted to give a little bit of a perspective on motion in low gravity worlds, referencing our human experience here on Earth. So here's two representative bodies of potential small bodies that we could visit with one of these rovers. And so your equivalent weight, how much you would weigh on an asteroid can vary from as much as a paperclip to a tennis ball, but you can start to get a feel for the amount gravity plays a role in your mobility approach. So there's a lot of challenges in transitioning from a rover designed for Mars or the Moon for a microgravity environment. And the one I just hit on was the microgravity environment. You have 10,000 to 100,000 times less gravity than you have on Earth. So traditional approaches that rely on traction or legged systems to propel yourself forward just simply are ineffective and uncontrollable. Remaining attached, this is an issue that was recently highlighted by the Philly lander, whose job was to actually stick itself to the surface and take measurements, but it inadvertently hopped, as I'm sure most of you know, over 1 kilometer and landed in the shadows. So it just tells us even a lander designed to stick itself to the surface has issues there. And aside from the microgravity, these bodies are characterized by very irregular shapes and surface topographies that you can see in this image returned from the Rosetta mission. Surface roughness like ridges, caves, monoliths at all scales. So I just wanted to show these images. These are the most recent images returned by Rosetta just 2 days ago, and they're actually really impressive high-resolution images. You can see all sorts of surface roughness here. This image shows some regions that look like they may be covered in deep beds of regolith. This image is, to my knowledge, one of the highest resolution images we've ever received from the Rosetta. It's a 50-meter scale at the bottom, and you can see what kind of looks like snowdrifts almost. The regolith may have accumulated in certain areas, resulting in this very uneven surface. So maybe I've scared you that it's impossible to move around on the surface of these bodies, but there have been a lot of approaches in the past on how to actually handle these challenges and design rovers specifically for the microgravity environment. And they can be divided into just 4 general classes. That's wheels, hopping, legs, and thrusters. Wheels and legs suffer from a lot of the issues that I just mentioned in terms of getting sufficient traction. There is a legged system that's being developed at JPL with microspine grippers, but they're very complex and sensitive to surface properties in order to anchor itself. On the other hand, you have hopping systems which really take advantage of the microgravity environment and understand that, yes, just like Philae, we're going to bounce, but maybe we can leverage the bouncing and the hopping to our advantage for mobility. But the downside of hoppers, at least the ones that have been developed so far, is that they're not very controllable. Just to name a few, the one on the top left and the top right are that's Minerva and Mascot, respectively. They're on the Hayabusa 2 mission, and they're going to be doing sort of a random motion. They each have internal masses they throw around, just basically to give itself a kick. So if it gets stuck or it just wants to relocate itself, it just kind of gives itself a random kick. But it's not sufficient for doing targeted sampling at different regions of interest. So we want to get, so the goal is to get the dexterity and capabilities of complex systems without having the complexity. So that brings me to our concept, which we named Spacecraft Rover Hybrids. It's a mission architecture that allows the systematic and affordable in situ exploration of small solar system bodies. And essentially what they are cubes that are internally actuated with flywheels, and they can be sized according to the scientific objectives, and they can achieve multiple modes of mobility by actuating these internal masses. And the key philosophy, as with all the other hoppers, is to exploit the low gravity environment, and instead of avoiding bouncing, try and bounce in the direction that you want to go. So here's a breakdown of just some of the general features. This is one of our prototypes. And so the mobility components are actually very simple. The internal masses that we use to get the momentum to propel ourselves are just flywheels. Flywheels, and we spin them with motors and then break the flywheels to create torques. So the subsystems for mobility are actually quite simple. They're the same kind of reaction wheels you would use in a spacecraft, just to achieve something a little bit different. I'll get into exactly how that translates to hopping in a second. But the key features of this system is, because it's internally actuated, it's completely mechanically and thermally sealed from the environment, which is critical for dusty environments where contamination of external actuators is an issue. It's symmetric design. It's a cube. It allows it to basically, it doesn't have an up or down. It can land in any configuration and move in any direction, regardless of how it lands. It has because the mobility system is actually relatively small, there's a large internal volume for scientific payload and subsystems, batteries and the like. And finally, it's minimalistic and scalable. So the basic concept behind how this thing actually works is you have 3 flywheels inside. This is a planar representation of what sort of a 2D side-on view would look like, but you spin up a flywheel to build up sufficient angular momentum, and then by applying a very rapid braking to the flywheels, you cause a jerk on the structure, and that jerk, when resting on the surface, allows it to dig its corners into the surface and propel itself forward. Without any external moving parts, you can get these very aggressive jerk and hopping maneuvers. So like I said, this is a 2D representation, but we'll have 3 flywheels inside, and the advantage of having 3 flywheels that are each perpendicular to each other is you can spin them at a combination of speeds, so you can get a net angular momentum in any direction that you want. So that enables a lot of different kinds of motion primitives that we can string together in order to controllably navigate to our destination. So hopping is the primary mode of mobility to get gross movement from one spot to a distant destination. And we can not only do that over a single axis, over a single pair of corners, but we can do it at any angle. And I'll show experiments later where we've been able to demonstrate this reliably. But we can also do more advanced maneuvers. Let's say you're at your destination and you need to point your science instruments. We can do controlled tumbling maneuvers. Let's say your X-ray spectrometer is located on a single face and you need to point that to the ground. We can controllably do that, as well as pointing and aggressive maneuvers to kick up dust to characterize the physical properties. So I wish I had time to go through more of like the dynamic analysis simulations that we've done, but I'll just highlight and say that we have done a lot of dynamic analysis models and simulation, and it's really informed a lot of the design of the prototypes that we've developed and how we control them. And so we've been able to get key insights into how to control specifically the distance of a hop and the angle at which we hop. And these will be key control variables for negotiating these very rough surface features on these small bodies. But the big problem with designing a microgravity rover on Earth, as a lot of you are probably thinking, is how do you test it when we're bound to a 1G environment? So there's sort of 3 approaches that we've taken, and they all have sort of complementary benefits and drawbacks. One is to over-design it for Earth. We do have a prototype that's next to our poster if you've swung by, and that one can actually move around on Earth. But there's a lot of limitations. You can actually get gross hopping, like very distant hopping, when you're constrained to 1G. The other is gravity offload test beds. These are test beds that basically offload a lot of the weight of the rover and allow it to basically go in parabolic trajectories at a much more reduced gravity level. So while we can get more distant hops, we still have to somehow mount the prototypes in some sort of gimbal system, which introduces some exogenous dynamics. So it's good, but it's not quite as accurate. The true test is to take it on these parabolic flights. I'm sure a lot of you know there's parabolic flights and drop towers, and they provide brief windows of reduced gravity where they fly in parabolic trajectories about 20 seconds away. So I'm going to go over some of the experimental results that we've done, that we've gotten doing these parabolic flights, actually just last month. We haven't had time to go through a lot of the numbers and analysis of this, but I'm going to show you a few of the videos of the experiments that we've done. So here's just a few videos, or a few pictures highlighting our experience. Like I said, this was just last month, so we were down at Houston, and we were given 4 days with 50 parabolas each day for a total of 200 parabolas. And during each parabola, we were exposed to about 20-second windows of 0G, or micro-G, I should say. Because the 0G actually fluctuates due to turbulence, we were able to leverage the brief periods where it was positive, because we actually need a little bit of positive gravity to keep ourselves grounded. And by timing the maneuvers just right, we were able to get a lot of really good data, actually. So I just have a series of videos that is going to show different maneuvers on different surfaces. So this is the cube hopping on a rough sandpaper surface, so it grips very well. We had about 4 different surfaces. You see the black one is sort of a grip tape. The yellow one is a slippery Kapton tape for maybe like an icy analog. The next video, this is a comet regolith simulant that's been developed at JPL, sort of to mimic a carbonaceous chondrite. It's a crushable material. You can think of it like a pumicite or a foamed concrete. And when the platform rotates, the spikes really dig into it and show the crushable properties. We also took the simulant and dug a big hole in it, because you're not always going to be sitting on a very flat and nice and flat ground. So how do our models and analysis that we've done for assuming a flat ground translate to very uneven surfaces? So you can see half the prototype here is hanging off the surface, but even still, it's able to rotate and dig its spike into the surface and still propel itself forward, which we thought was pretty amazing. So we were also given a set of parabolas in the flights that were positively biased. This was important for testing actual granular media, because in the parabolic flights, typically they aim for 0G, which can briefly go negative. And if you have a sand pit, for example, it could fly everywhere. So a handful of parabolas per flight, we were given positively biased gravity. And so we had a box that contained coarse sand. And this red sand behaves more like a fluid in 0G. It was very interesting to see how the rotation of the platform really scooped the material and sort of flung it back in this spectacular fashion. Yeah. Here's just to show that we can hop at an angle. This is over a single spike. And for all of you lunar enthusiasts, we were given lunar level parabolas and showed that we could indeed hop, not as far, but still hop in lunar level gravity. And so we also demonstrated more advanced maneuvers, such as tumbling. This is, again, if you needed to point your science instruments, just changing your orientation. This is a heading control maneuver where we do a yaw maneuver and just quick little jerk can get us pointing in the right direction. And then finally, this one's one of my favorites. We call this the tornado maneuver. This one is sort of what you might use if you were to get stuck in loose regolith. You can imagine if you're coming into the surface with higher speeds, you could get embedded in the surface. And these aggressive maneuvers, as you can see here, really fling the material in a pretty spectacular fashion. That could also be used to just characterize the physical properties intentionally, not even if you're stuck. Just do a quick spinning maneuver and kicking up the regolith with the idea of observing its behavior. While the mobility system is interesting in its own right, this is ultimately a spacecraft, and its job is to do science. So we've baselined a system architecture for a reference mission to Phobos. Phobos is an interesting target for a lot of the reasons I described before. It's spectrally diverse. So the current design is the 8U design, although it's scalable anywhere from 1U to 27U, depending on what your scientific objectives are. It's got all the standard subsystems like avionics, telecom, science instruments, obviously, sensors, actuators, and electrical power. And thankfully, because of its cube-like form factor, we were able to leverage a lot of the subsystems that have already been developed at JPL, for example, NESF, Inspire, Lunar Flashlight, and the Marco mission. They've all developed CubeSat form factor subsystems that we could very easily package into this volume. The current battery design is baseline for just primary batteries, which would give it a lifetime of anywhere from like 2 days to a week. So in conclusion, robotic exploration of small bodies, as we've heard throughout this forum, is a main focus of NASA and will be in years to come. But in order to get the in situ measurements to complement what we know, we really need disruptively new mobility approaches from what has already been done on Mars and the Moon. The spacecraft rover hybrids that we propose is a new paradigm for controlled mobility on small bodies to offer new science at an affordable cost. These are targeted as secondary payloads for missions to the Mars system, so they can be affordable. The proof of concept was demonstrated, as we saw in those videos. And the current and ongoing work we're working on is really embedding a lot of autonomy into the system. So you're going to have very intermittent comms with the platform. So how does it autonomously decide how to navigate to a remote destination on its own without a lot of human in-the-loop interactions? And obviously, and we're also doing more mission formation trade studies for armed targets or prospecting for resource utilization. So with that, yeah, sorry, I'm getting kicked off the stage. Take any questions if we have time.
Right. That was great, Ben. Thanks. That was really great, but we do have to get this done pretty quick here now. All right, the last presentation is by Harlan Spence. The title is